Happy National Robotics Week and welcome to Nonlinear and Autonomous Systems Laboratory. I'm Nina Mahmoudian, Assistant Professor of Mechanical Engineering and Director of NASLab. While in NASLab, we work with robots. That's why we are giving you a tour. We are developing algorithms for long-term operation of robots. And in all the work that we do, we develop our algorithms, we implement them on real robots, and we deploy them in real world. And what a great opportunity. We are in Upper Peninsula, Michigan. We have long winters and we have Lake Superior in our backyard, and not only we have water in our backyard, we have ice covered water. So we think about the challenges that robots face when they are working. And speaking of water, we better start our tour with our underwater projects. So we develop our own low-cost, highly maneuverable, autonomous underwater vehicles. I have here Brian Page, a PhD student, and Donna Fard, a PhD candidate, who will explain to us what is Rafi and what it does for us.
Okay, so basically, as Dr. Moumoudine said, this is the Rafi. This is the research-oriented underwater glider for hands-on investigative engineering. Basically, that means that it is an underwater glider. So it is an autonomous underwater vehicle that is propelled based on changes in buoyancy. So basically, because it's an autonomous underwater vehicle, we deploy it in Lake Superior. And when it's deployed, we have no way to contact it, no way to control it. It controls itself. So we don't actually have like someone operating this vehicle. And because it's a glider, it doesn't have a traditional propulsion system like propellers or thrusters. Instead, it goes and uses a ballast tank and buoyancy to actually propel itself through the water. So basically, this vehicle sits neutrally buoyant in the water. It sucks a little bit of water into this ballast tank down here, and that causes the vehicle to sink. And then as it's sinking, there's a wing at the rear of the vehicle, which causes it to go and fly forward. At the bottom of our glide cycle, we pump water out of the ballast tank, which then causes us to float, and again, the wing causes us to go forward. So basically, we're going through the water in a sawtooth motion pattern, and this is extremely efficient because we basically only really use power when we change our ballast position, and the rest of the time we just sort of sit there and wait. In order to control where we're going, we have a mast here that we move forward and backward to control our pitch, and then the entire vehicle is mounted on a rail, which controls the roll of the vehicle. So basically, as we're flying through the water, we're able to go and roll the wing, just like an airplane, which causes us to turn. So using this system, we're able to achieve a 3-meter turn radius using this vehicle, compared to every other underwater glider has a turn radius of about 30 to 50 meters. So our vehicle is much more maneuverable, and it's also a low-cost vehicle. The maneuverability and low cost is critical for where we deploy. We're deploying in Lake Superior and enclosed waters, because we need to be able to deploy in these enclosed spaces in shallow water. And it's hazardous, so we need to be a low-cost, maneuverable vehicle so we can actually deploy this. And we also, just to give you a sense of like the endurance of these vehicles, a vehicle slightly larger than this went from New Jersey to Spain on a single battery charge a few years ago. It took it like 6 months to get there. But basically, because of this buoyancy drive system, they're extremely efficient and are able to go and travel for long distances very efficiently. This enables them to be used for long endurance environmental monitoring missions, such as doing climate change measurements, doing water quality sensing, and we've actually performed missions like that using this EcoPuck, which this is a chlorophyll measuring tool. So basically, using this, we can measure the algae content in the water and collect that data and then give it to the Great Lakes Research Center scientists who are able to analyze that data and tell us about the quality of the water. And now Donna's going to talk about maneuverability and a few other things.
Well, so when Brian talked about turn, in glider's sense of motion, turn is a helix or a spiraling motion. So imagine a free fall of airplane that your glider start the motion and you don't consume any energy. You just use gravity and go down. Or we have a solid motion that the glider goes forward, down, and up. So far these are the two motions that all gliders they share. But what we are doing here is to linking these two together, because Our glider is specific to shallow water and crowded area. To maneuver there, you have to be highly maneuver, and we're using those linking a part of that spiraling as our turn to our linking maneuver, so we can manage to go through obstacles. So that's what makes this glider very interesting. Of course, we are low cost, and this is built in Michigan Tech, at Michigan Tech. The design was part of undergrad program, and then grad student, they came along and then developed different algorithm for control and maneuverability. We test this glider in a controlled environment because shallow water testing has to be in a controlled environment. So we use STC swimming pool at Michigan Tech, and the maximum depth we get there is 4 meters. So we basically are simulating and modeling our motion in a swimming pool, and we can do that 3-meter turn radius that Brian was talking about in the swimming pool. We have tested over 200 hours to make sure that we test all the functionality and all the maneuvers that we want to, and then we take it out to the Superior Lake and we test it in a real open water. Of course, in a lake, because our glider is specified to lake, and we have tested it last summer, and just one glider. This summer we are going to test 3 of these, so multiple glider, and then we will test our coordination algorithm. So 3 gliders are going to be underwater. They're going to sweep a mission area and use these sensors. Could be any type of sensor. We have choreography A here, and we measure the choreography A, and we give the data to scientists so they can study the algae. So our responsibility is get the data for them, and then they study and analyze the rest of it.
So you always succeed in your missions?
Well, no. Well, it's so one. well. I have a good story.
Stories.
I have a good story to tell. But so last summer in August, we tested this glider in the Superior Lake because our testing is untethered. So we don't have any tether connected to glider. So when glider goes underwater, you have no control, and you have to wish that the glider comes back up. So one of these time it did not. We have a small switch failure on our buoyancy tank. So glider stayed underwater for over a month, and we did some search algorithm, and we had a beacon. Well, we foreseen that we might lose it because it's untethered. So we had a beacon on the tail part of our glider, and when we lost it, we used the hydrophone to listen to that beacon, that where our glider is. And it took us a month because the portage canal was muggy and not very clear, so it's not easy to see underwater. We triangulated the position and used ROV, and at the end divers to save this glider. As you see here, this yellow piece is, you can see the dirt. This is a souvenir from our last glider. We saved our glider, we salvaged few parts, but then we had to build another one. Having a low-cost glider is good. You can build another one very quick. Well, we kept this part to remember that you can lose gliders. And so hopefully this summer we are not going to lose it. We have remedy actions. So if that happens again, we'll save it less than a month, because beacons have limited time life. So our beacon was 45 days worth of life. So we got it on time. But it was a good experience. It was a good summer. Field testing has its own challenges.
So yeah, we build, we deploy, we gain knowledge, or we lose some and we repeat it. So this is the engineer process that we practice with all the projects that we do. Another project that we have is creating power distribution systems or mobile microgrids. Imagine in power grids that we get electricity in our houses if we have failure. In case of failure, because these systems are very centralized, they are very dependent on personnel for repair. What we are doing here, we are thinking that can we make these systems decentralized, and can we have them mobile to deploy them in case of emergency. And if we do that, then we are going to have mobile robots that they carry different components of the system. One can be cabling robot, the other one can be a power converter, or some of these robots can carry even renewable energy resources. And what they will do is that they're going to work together and they're going to connect power sources to power loads. And the application will be for disaster recovery, but more importantly, it can be for forward operating areas. I have a great team of people that they are working on this topic. Farzin Mouridian is a research engineer in NASLab. Nathan Spike and John Naglak, they are first-year PhD students, and they're going to explain you the details of this exciting project.
So here we have a ClearPath Husky. We have 4 of these in the lab, which we can use to run our microgrids demos. They're small enough that we can run demonstrations in the lab, and they're also capable of off-road travel, so we can take them outside and run microgrids in an environment that's more similar to what we'd see in the real world. We're actually going to take them outside for the first time later this summer, so we're pretty excited about that. It's a versatile platform. We can add components to it as we see fit. It basically comes with just the bottom here, and we've added these top plates. We've also added a cabling system to this robot, a 5-axis robot manipulator, and then also a vision system. And that's what allows us to make electrical connections here within the lab. The robot also has a package of sensors that allows it to perceive its environment around it as well as its motion within that. At the front here we have a LiDAR. That works by bouncing light off of objects surrounding the robot and detecting distances, so the robot can determine whether or not there's an obstacle that it needs to avoid. We also have a GPS unit for outdoor use, and these markers here are associated with our motion capture system, which we use to localize the robot indoors, which John can actually talk more about.
Yeah, localization is an important problem in robotics. It's the challenge of determining the position and the orientation of our agents, our robots, as they move through their environment. There's 2 challenges that we come in when we do the localization problem. One is uncertainty. How confident are we about the measurement we have of the position of the robot? The other one comes from disturbances. Is there something interrupting the signal or creating higher uncertainty than usual? When we're using the GPS system, we depend on satellites that send a very weak signal to the robots. It has an uncertainty on the range of meters, which means we might think the robot's here, but it's actually maybe across the room. And that's quite challenging in the outdoor environment. And it's susceptible to disturbances from things like trees and buildings, so they're very common. In fact, we can't get a good GPS signal indoors. That's why we depend on a Qualisys motion capture system. You can see that there's cameras mounted on rails around the lab. These cameras illuminate the whole lab with infrared light, and then they take a measurement and they triangulate that. Over here we can see the positions of the agents on this computer screen. There's a local coordinate reference frame assigned to each of the robots. We get an uncertainty in millimeters on our positioning, which means it's very easy to run our demos here. We use this data in a number of algorithms that Farzin is going to talk about for path planning.
So to be able to have this mission operate, we need to have the robots make decisions autonomously without human intervention. And after having the information about the location of the robots, we use the laser rangefinders that we have in front of the robots to get an understanding of the environment and where the objects are located and how they are moving in the environment. Using this information, we process the environment and do path planning to find trajectories that will take us from the current position to the destination that we want to go to. This is not the only application that we use the ground robots in, and Dr. Mahmoodian will talk about the other.
So whether we are underwater or on ground, or maybe we are in air, our robotic operation needs precision and persistence. And persistence for robots is limited with the battery life. And the other project that we are working on is developing a mission planning architecture that really balances the robot battery life with the mission specifications. And Bing Zili, who is a PhD student, is going to talk about the algorithm development. He's working with Berzin to develop the algorithms, and then they implement those algorithms and they validate their work. So I have Bing explain what is the details of the project.
I've been working on multi-robust mission planning for long-term missions. Long-term missions usually have large, huge mission area or takes a long time to cover. So for the underwater scenario, we can take the example of finding MH370. You can see it has huge mission area of 860 kilometers square. And an AUV called Bluefin 21 was deployed to cover that mission. The battery life of Bluefin 21 is up to 25 hours, and it took more than 20 days to cover that area. So just imagine how much we can improve the efficiency of this mission by deploying multiple robots. So that is also very challenging because now there's no technology that can solve this complicated problem, and this is what we are working on. So we have two approaches. I'm gonna show you two short videos. So the first one is using mobile charger. In this scenario, it's a boat. The boat travels fast and it can do the battery swapping to the AUVs, but at the same time, it's very expensive. So for the mission that will go over and over again, I'm gonna play this again. We can replace the boat with a charging station. But as you can see, the AUV needs to go to the charging station and go back to work. So it also causes some energy waste. Another approach is that we're developing an underwater mobile charger so it can get the AUV recharged. And then our approach is very general. It doesn't limit to the underwater scenario. We can also apply that to ground robots, area robots, and we can consider the obstacle in the area. This is the simulation figure. We can also include the priority in the area, and also we can consider the wind, the disturbance, or the current in the mission area. So depends on what sensor that robots may carry and the real case problem, we can scale up our problem to very high resolution for the same area. We can apply our method to different mission type and different kinds of robots. So we're really looking into solve the recharging problem for multiple robots, considering real life constraints.
And then Berzin is going to talk about implementation.
We are trying these developments on hardware to evaluate how they perform with real life constraints. What we are doing is that we have aerial robots that we make them track the trajectories that come from that simulation. What we have here is a hexacopter that has an onboard computer and a flight controller, and it communicates with the camera system that we mentioned before with these markers that are installed on it. We have these robots move in the area, and they land on charging stations to simulate the whole simulation process. We experiment with both stationary charging stations and mobile ones. For the mobile ones, we put the charging stations on the ground robots again and have them move in the environment to try different scenarios. We are not going to demo these today, but
Yeah, so as you noticed, we are working in air, on ground, and underwater. And we not only do research, but also take our research to classroom. And that's what it really excites us when we engage future STEM learners and maybe future robotic enthusiasts. So one of the things that we do, we take our underwater glider work to classroom. We are building low-cost educational underwater gliders, and we engage middle school and high schoolers. you now need to go and register for summer use program, and we have scholarships available. So I'm pretty sure after Vilnis Stambaris, who is an undergraduate researcher in our lab and is working on developing Guppy, and Donna, who will explain our program, our summer program, I think you will be very excited and intrigued. So Vilnis, take it away.
So this is Guppy. This is our low-cost high school and middle school education platform. We make this out of easily found components, and down here we have our buoyancy engine. We make that out of a servo, syringe, and a couple 3D printed parts. We control that with our Arduino, and while we're trimming, we control the Arduino with, or we control the pump with our remote control here, and we can make it go up and down. And we use that to figure out how many weights we need to put on our bottles to make them neutrally buoyant. And then we put all of these components into the bottle, hit run, and that will make our bottles go, make our pump go up and down, and that'll make our bottle go up and down, and we use these fins to translate that up and down into a forward motion. And these things cost about $50, and I'll pass them off to Donna to explain the education program.
So we are offering these guppies in our summer use program. It's a week-long program that we offer this version to middle school students, and we will teach 101 electronics, 101 programming. They learn how to program this Arduino boards. They learn how to solder, how to put components together and build a robot. Then we take these robots and we will program that sawtooth motion of underwater gliders. We help the student to develop that algorithm so they think in an engineering way. So we teach them not only how to build a robot, also the way of engineering design throughout this week. And then after they build everything, they will start bench testing on the 4th day to make sure that their buoyancy engine acts as they expected. After we're sure that everything works, then we put these buoyancy engine inside the bottles, and we run a leak test to make sure the water doesn't go in the glider, and it's safe to take it to the 5th day, which is our swimming pool day. Students go and they swim with their guppies, and to make it more interesting, we will give them cameras to mount on their guppies, and the guppy, they can record their experience from guppy point of view. So they can have that video as a souvenir of that their 1 week experience. And we are going to offer these guppies again this summer. So I really suggest you go right now and sign up for our program. You have a scholarship. I'll be one of the teachers. Vilnis will be there, and we'll have so many enthusiastic kids that they love robotic, and they love underwater marine vehicles.
Yeah, so with Guppies, we teach kids and other students that robots can be helpful in everyday life, and it can help us collect water samples and learn more about our environment. So whether you are outside swimming in Lake Superior or doing other activities, look out for our golden roughies in lake, and also look for our yellow huskies that they're gonna do experiments outside. And well, I cannot say enough about our hexacopters coordinating with our ground robots. So we are going to be very busy this summer. Come visit us at Michigan Tech, take our autonomous courses, get excited about robotics, and come see us in summer because it is gorgeous outside and we are going to work outside. And what a better way to spend our time, work on science, do implementation and technical work, and enjoy beautiful summers in Upper Peninsula. Thank you very much for having a tour of our lab, and happy National Robotics Week.